is Alex Brimhall, and I'm going to be talking to you today about the contribution of Lifshitz-Van interactions to the surface energy, or gamma T, of silicon 100-based surfaces using the Van Oss-Young-Dupre model. I'm an undergraduate at Arizona State University, and I'd like to take a moment to thank my colleagues, MASCARENO, Andrew Davis, and Dr. NICOLE, both from Arizona State University, as well as our high school researchers, BADE from Brophy College Prep, and NITHIN, KANNAN, ABIJITH, KRISHNAN from Basis High School. I'd also like to thank CLARIZZA Watson and SIO2 Nanotech LLC team for material support. So before I continue on with my presentation, I want to point out something you might be unfamiliar with, and that's this silicon 100 right here. This is a Miller indice, letting us know that the structures that we're dealing with are crystalline. And the 100 indicates that when we're looking at the planar surface of our wafer, it's going to be in this sort of orientation. This is what our crystal structure is going to look like. My colleague Ashley presented on her analysis of surface energy of thick silicon dioxide layers. I'm going to be doing a presentation on thin dioxide layers. So what is surface energy, and what is it used for? Surface energy, or gamma T, is the energy of interactions between the surface and any materials above it. And this is due to three separate things here. First, our atomic species and our geometry. Essentially, what's in our sample and how is it oriented. Also, electron acceptors and donors. Electron acceptors, quite simply, accept electrons, and donors donate electrons. These can be atomic species like ions that reside within a surface or in the materials above the surface that they're interacting with. Our research is going to be focused on the ones that are above the surface. And we denote these as gamma minus and gamma plus. Third thing that contributes to our interactions are these molecular dipoles, or gamma Lifshitz-Van, gamma LW. We can explain this sort of interaction using our water molecules. Water is an excellent electrical dipole. So we have very positive hydrogen on this side, very negative oxygen on this side. And so due to their molecular attraction, we're going to align in an anti-parallel orientation, sort of like this. And so our Lifshitz-Van Waals contribution to surface energy is essentially this sort of electrical molecular interaction, but this is with the things that are above our surface and with our surface. So molecular interaction between the two. That's of this nature. Surface energy is typically measured through a wetting process. And so what we do is we wet the surface with a liquid, and we see how the molecules in that liquid interact with the surface, and that'll give us an idea of, what our surface energy is. And so the three liquids that we're using two polar, water and glycerin, and one non-polar, which is alum, bromine, naphthalene. And as my colleague Ashley said, these are two very well characterized, or three very well characterized liquids that are going to behave with the surface differently. So we have our total gamma T, our total surface energy, and that's from these three different interactions. Our Lifshitz-Van Waals, our acceptors, and our donors. Our surface energy measurements are used in a process called hermetic nanobonding. And this is surface bonding at the molecular level in order to seal things from fluids, and that could be a gas or a liquid. This requires anatomically smooth surfaces in order to avoid percolation. And so, in order to nanobond, we need to be able to control our surfaces at the nanoscale. We have two separate requirements in order to do that. First, we need planar surfaces, as mentioned earlier, because at the nanoscale, surfaces are quite jagged, even though they may look smooth to us. They've got ridges and valleys, and so if we're trying to bond two of them together, we may find it's like taking two pieces of a jigsaw puzzle from opposite ends. They're not going to mesh nicely. So they need to be planar so they can go together like this. Also, we need to make sure we know the chemical and hydroaffinity of the surfaces, so essentially how they're going to react with other things. We want to make sure they're compatible. So we have a surface that's more prone to donate electrons, and a surface that's more prone to accept electrons, so that we can have some nice cross-bonding. So this has application in single device medical implants. We're focusing on the permanent glucose sensor in order to seal it from saline percolation. But this also can be used in marine and air integrated sensors, as well as solar and panel encapsulation, and we're working with tandem solar cells. So in order to quantify surface energy components, we need to take a look at some equations. For a qualitative analysis, let's turn our attention to these images surface-liquid interface with very high contact angle. This liquid is interacting more with itself than it is with the surface. For the hydrophilic or water-loving droplet, we have a very low contact angle. It's interacting a lot with the surface. So to look at our equations that sort of developed our theory, we have Young's equation, which gives a very simple relationship between our contact angle and our solid-liquid interface surface energy. And we are able to relate those two together using the solid surface energy and the liquid surface energy. Van Oss's theory is a bit more complicated and a bit more specific to our silicon wafer analysis. And so that gives us a way to determine gamma T through our Lifshitz-Van and our electron donors and acceptors as well. So we use the Young-Dupre equation, which combines both the Young equation and the Van Oss theory. And so here we have a very simple relationship that includes our electron donors, acceptors, and Lifshitz-Van contribution, as well as our contact angle here. So what we do is we measure our contact angles that were created by our three liquids and our silicon surface, and then we have an equation for each, and using a system of equations, we solve for our three unknowns in order to compute gamma T. Now it's important to note that this equation indicates that a higher contact angle will yield a lower surface energy, and vice versa. So our laboratory conditions were extremely important and extremely well regulated. Since we're working with measurements of interactions at the nanoscale, it's very important that we have a low particulate environment, because particulates can seem like boulders on the nanoscale, even if they're really tiny. So what we used a class 100 flow hood, which means that we have less than 100 particles per cubic foot. We also have class 10 gloves and arm sleeves. Typical PPE such as a face mask, hairnet, and eyewear, which you can see here. We have sterilized lab coats, as well as sterilized glass syringes and beakers, which were sterilized with 18 mega OMDI water. Our experimental procedure was relatively simple. We would put water droplets on wafer and take a picture of them, and then reorient the camera and then put glycerin drops and take a picture, and the same with alpha bromonactylene. And then these pictures were uploaded and analyzed and fit with ellipses, such as this one. And this is the droplet, and this is the reflection of the droplet right here. So there were several different sorts of wafers that we analyzed. Each of them started off as an RCA clean here. And RCA clean is a way of treating wafers developed by the Radio Corporation of America, in which it deposited a oxide layer on top of our surface in order to keep it from interacting with different things. We analyzed one wafer like that. Another wafer was annealed via rapid thermal anneal, or RTA, which deposited another slightly less disordered oxide layer on top of the RCA clean. The other wafers that were analyzed were treated with this Herbo-Lurie process, which is a patented treatment process by my academic advisor, Dr. NICOLE, as well as Lurie, in which they strip the wafer of the amorphous oxide layer and deposit a very ordered 2 nanometer oxide layer on top. And then one of those was analyzed, and then 2 oxidized ones via RTO were also analyzed, which deposited another 2 nanometers of oxide on top of it. The experimental innovations we did to separate our work from others was to use regulated high-resolution imaging for consistent and high-quality analysis. Also, we did not use tangent lines in order to determine our contact angles. We used Cecil drop analysis, in which we modeled this as the top of an ellipse, and then fit an ellipse to both the droplet and the reflection, and then used the dimensions of that in order to determine our contact angle. The 6 microliter droplets are very important, as other ones will get, larger ones will be affected by gravity. Also, again, we have 4 contact angles per droplet, and we use many droplets on our surface in order to improve statistical significance and test a larger portion of our area. Also, we made sure to rotate drops that were warped through our camera, and to make sure that they're horizontal so that our ellipse fit would be accurate. So what's our model and what are our results? Here we have all of our samples here ordered by hydroaffinity or by increasing contact angle. And then here are our models. We have our RCA amorphous on top of our silicon surface, and then this is the RTA on top of the RCA. Our ordered Herbo-Lurie surface, and then again the RTO oxide on top, and then our HA. We can see that our contact angles increase as our defects decrease. And have surface energy, which decreases, and then 90 degrees minus contact angle, that's in red. And so we can see that as our contact angle increases, our surface energy decreases, which is consistent with the Young-Dupre model, which we had earlier. To make that more clear, here we have total surface energy versus contact angle. As far as components go, our Lifshitz-Van Waals is very consistent. While we can see that our electron acceptor component here in purple is a lot higher in the RCA surface, which is very defective, and a lot lower in the Herbo-Lurie surface, which is extremely ordered. To take away from our top, we can see that our total surface energies were measured reproducibly. So our sigma was about 5 to 10% and consistent throughout each of the analyses that we did. Also, our total surface energies can detect structure change. So our highly defective RCA surfaces had a much higher surface energy, while our Herbo-Lurie had a very small one. Also, our accuracy of analysis decreased as hydrophobicity increased, so our higher contact angles were more difficult to fit via Cecil drop analysis, and so they yielded a greater error. Also, our contributions from Lifshitz-Van molecular interactions were the largest in the ordered, and it was about 100% of our gamma T versus our hydrophilic surfaces, where it was only about 76.5. And in conjunction with my colleague Ashley's talk, we can see that our results were fairly consistent between our thick silicon dioxide surfaces